I think I can start. Sounds like everyone can hear me. Welcome to the first session of the morning. I'm glad you all chose to learn more about App Engine, in particular Appstats, which is a tool for App Engine developers, either Python or Java, to learn more about the performance of their application. So, quick overview of the talk. Note the Wave URL and the Twitter tag at the bottom. Please use those for any interaction. I'm going to give a little bit of a demo introduction, a demo of a tool, of course, some background, what you would do to write your own tool like this, because there's actually not really any magic involved, how to configure it, how to use it, and then hopefully I will have plenty of time to talk about a number of specific performance issues that we found in various applications that I wrote or colleagues wrote or customers, early users wrote, where Appstats turned out to be very helpful for performance analysis. So the higher bit of Appstats is it's a tool library that you link in with your App Engine application. It is specific to for App Engine, and it analyzes your mode procedure call performance. It's available for Python since February. It's available for Java since March. The tools work the same. They have the same user interface. The actual implementation that is linked into your application is somewhat different. This is a very quick graphical overview of the main timeline view that gives you most of the insights in your application. From here on, you can also drill down to specific things like stack traces corresponding to each call. Basically, it shows you what the total time was taken up by a request, what RPC calls it made, and where those RPC calls were relative to the timeline, and how long they took, of course. And then the red bars show you how much you were charged for each of those RPC calls. Some basics, as I mentioned, Appstats is a userland library. It's just linked with your application. There is no special system calls, no support in the App Engine server for this tool specifically. It has a little bit of runtime overhead. I'll get into that more later. I think the runtime overhead is pretty minimal. The APIs it uses to do all its instrumentation magic are existing APIs that had been added to the App Engine APIs long ago. Some of the instrumentation APIs it uses are actually standard Python APIs. Others, for like measuring things specific to RPCs, are App Engine specific. There's no need to download anything. This is part of the standard software development kit that you already have when you start developing with App Engine. I mean, that's your only download. There's no extra download just for this tool. You do have to do a little bit of configuration. If you're using Java, it's about 10 lines of XML. If you're using Python, it's about 4 lines of Python and 2 lines of YAML. And finally, the user interface for this tool, and that is somewhat unusual perhaps, but suitable for something that is self-contained and all userland code. The user interface is actually part of the library. What is the main thing you can do with Appstats? I would say probably the most important thing you can do is find which parts of your application, which specific request handlers are expensive, and which RPC calls, for example, a particular database query or a call to send email or fetch an external URL, are the hottest parts of your application. And so if you're taking Don Knuth's paradigm to heart, which says avoid premature optimization, you write a correct application first, then you tackle optimization, and this tool shows you where to start doing that optimization, so you only have to touch a small amount of your code. Now, Appstats records everything about every single remote procedure call made by your application. In App Engine, pretty much everything is a remote procedure call, whether it's sending email or fetching an external URL, or making a call to the datastore or even memcache. All those things are considered RPCs. The tool shows you, as I already showed briefly, shows you a timeline of individual requests. It also shows some overview of sort of global statistics. How many requests of each type did you get? How many RPCs of each type did you make? And sort of a combination of which which requests caused most of the RPCs of each particular type. The timeline, in most cases, is the most important tool to find out where the time actually goes. And the Python version, at least, lets you drill down to the contents of stack frames so you can view local variables, which is often very helpful in finding out why a particular call is being made. So now it's time to go do a little demo. I'll start actually, okay, always a little tricky to find the right window. Okay, this is an application. It's called Rietveld. It's also called Code Review. It runs on Appstat. I wrote it about 2 years ago, actually, as a demo for App Engine. It has a number of interesting features. It allows you to, let's see how fast it is. Yes, it allows you to view patches, comment on them. I'm not going to go into much detail there. The important thing is that we have an Appstats window connected to this application. I have sort of, actually months ago, I linked Appstats into Rietveld, and all I have to do now is go to the stats URL and see what the most recent statistics were. This is a pretty overwhelming window, I'm afraid. Let's see if I can find a smaller version of this. Yeah, this is an earlier snapshot that I took this morning after resetting the data collection briefly. So we have 3 sections of the overview UI. On the left, we have everything ordered by RPC calls, so datastore next, datastore get, datastore run query. On the right, we have everything grouped by particular calls into the application. So slash is a popular request, repos is another one, and then various diff-related requests also happens. At the bottom, we see the entry point to the next important part of the application, which is this is just a log of recent requests. So actually, this snapshot was taken a few seconds after I reset the data gathering, so the log only has 7 entries or so. Let's go back to the current one. So we scroll down, we see that there have been a lot more calls since this morning. Okay, here we have some of the more recent requests. I think this is probably going to be a nice one. So here we have a timeline of this particular request. At the top, we see the request that causes this particular sequence of events to happen. On the left, we see exactly which calls it made. It made a memcache set call. It made a datastore get call. It ran 4 different queries, and somehow the second query always comes out by far the most expensive. So it would be interesting to drill down on that. So let's click on that second query. You can click right there, and now it opens the stack frame. This is actually still the same window. It just scrolls down to the corresponding sequence. So here is another view of all those RPCs. Again, the memcache set, datastore get, but here you see more detail. You see the contents of the request buffer, the content of the response buffer, and then the various stack frames. So, well, datastore.py is some internal library. db-init is another internal library. This is actually a library that you use to interact with the datastore. Typically, the datastore.py is a lower level library. Then here, views is application code. Let's see what was on the stack. So we see some local variables, drafts, issue, patch set ID. If we want to know sort of where this lives in source code, we can open that, the source code in a new window. And there is our small little primitive source code browser. So we can see that all those variables, like issue, comes directly into the query. So if we go back to the top, there are a few other things that you can see about this request. Oh, by the way, if you were to click on this link, it would actually send another request like that to the server. So this is that particular view. There is, I don't know who looked at this thing, it wasn't me. So there are a couple tabs. The RPC stats shows you how many calls of each type it made, how much real time was spent in each of those calls, and how much time you were charged for each of those calls. Then there's the CGI environment, which shows you basically the headers and some other information. If you're using Python, you'll be familiar with this. From this, you can reconstruct the entire request, like the host header had this value, this was the referrer header, the user agent header, and so on. And finally, in some cases, it's kind of useful to know exactly what the search path for Python modules was. And so you can see that here. Back to the timeline, and now back to the presentation. I should mention that the Java tool has a very similar user interface. You'll see that the CGI environment and the systl-path part are not present in the user interface. I'm not giving a live demo of the Java version. However, you can hear more about this tool in a Java context in tomorrow morning's talk by Don Schwartz and Toby Reilts. And by the way, I heard in the keynote this morning that the Java version of Appstats has also been integrated in SpeedTracer, which is, in general, a browser-side performance analysis tool that has a similar graphical user interface as Appstats. SpeedTracer has an optional integration with Java Appstats on the background. And there's another talk going on, which unfortunately you've already missed because it's going on simultaneously with this one about SpeedTracer, but I'll also show that off a little bit. So a little bit about the background of Appstats. It's important to understand exactly what a remote procedure call is. In the App Engine environment, in the context of App Engine, it's a very clearly defined thing where it's a round trip between your application and something in the back end. Now, that something in the back end could be Google's mail service and infrastructure. It could be the App Engine datastore. It could be the Memcache server dedicated to your application. It could be any number of those things. It could also be an external website that you're accessing through the URL fetch interface. All those things are RPCs, and all those things are recorded by Appstats. So it's not limited to database calls. I should mention that in the case of database calls, and I think we actually saw an example of that, if I can find that window quickly. Yeah, here these datastore next calls, they're actually, in a sense, continuation calls for large queries. If a query returns under 20 results and under a megabyte of data, all you see in your RPC stats is a single run query call. If your query is larger than either of those numbers, more than 20 results or more than a megabyte of data returned, because of limitations in how many results you can fetch at one time in one response, it's actually broken up into multiple calls, the first one of which will be called run query, and all the subsequent ones will be called next. In general, if you see a lot of next calls, you're probably doing inefficient queries because it's unlikely that one single request in your application is interested in hundreds of query results. You're probably doing some kind of computation that you could do offline more easily. Anyway, why did I decide to write a tool whose only purpose it is to instrument remote procedure calls? Well, looking at the timing, if you look at the typical web application running on App Engine, you'll just notice that almost all your time, and again I'll just sort of show one of our Appstats windows, almost all your real time goes to waiting for queries or other remote procedure calls. The only place in this graph where there is significant time that is not spent waiting for an RPC is somewhere here. And I imagine that this is where it's actually doing some template expansion. But that's a very small fraction of the total response time of this application, because this took over 800 milliseconds to compute, and almost 700 milliseconds of that was pure RPC time. So in a sense, I have to admit that Rietveld, even after 2 years, is not all that optimized, which makes it a great topic for this presentation, of course. So some statistics just to give you a feel of how fast App Engine is, and you can use Appstat to measure these numbers for your own application. Writing a single entry to the data store is 50 or 100 milliseconds, and actually the size of the entry is barely important. What is much more important in determining how long it actually takes and also how much you're charged for it is actually the number of properties in the data that require indexing, because the index updates are part of the write. Getting an object, of course, if you know the key, is much faster, but it still takes 10 or 20 milliseconds. A query, the fastest queries I've measured were about 20 milliseconds. I've seen them vary between 20 and 100 milliseconds. If you're doing complex queries, comparing a number of different properties using multiple indexes, even a query that only returns a few results can take half a second sometimes. Memcache is probably the fastest API we have, the fastest RPC. Even a Memcache call, a one round trip, can be 5 or 10 milliseconds. The fastest I've seen is about 4 milliseconds. And realize that Memcache is just copying a number of bytes and a single hash table lookup. There's no I/O that goes on. So all the time, all that 5 or 10 milliseconds that you spend waiting for Memcache is purely network traffic. You go, your application makes the call, the data is sent to the Memcache server. Once the Memcache server has received the last byte of your request, it does its work, copies the response in the output buffer, and then sends back. And all that time you're waiting. The actual, I haven't measured it, but I imagine that the actual time spent in the Memcache server doing real work is probably something like 10 or 100 microseconds. And everything else is just waiting for the data to get from here to there and back. Even though this is all, of course, within one Google data center using the fastest networking hardware available in the universe. So anyway, because App Engine applications are very networked, every operation you do, whether it's Memcache or datastore or something else, goes out to a server that does the actual work for you. The typical application is slowed down by how many remote procedure calls it makes more than by any other factor. I mean, if you're thinking about traditional optimization of your application, you might think of things like, oh, I'm using an n-square algorithm where I really should be using a log-n algorithm. That is not the important thing in optimizing your web apps. I mean, well, yes, it could be, but it's unlikely. It's much more likely that you're making 10 RPC calls to get the same object over and over because you have some bug in your application, or you're making 10 RPC calls to fetch 10 different objects that you could just as well fetch in a single batching RPC call. So this is why RPC instrumentation is so important and why I recommend that you all try this out. So what does Appstats use under the hood? How is it implemented? I had way more information about this, but I decided that there wasn't enough time in my talk. I don't want to go 30 minutes over like the keynote. So the one thing I want to mention, there is a general feature in App Engine, general API called call hooks, where any part of user code can register a user function to be called right at the start of an RPC. And it gets the function is called with a number of arguments that tell it exactly which kind of RPC is being made and which request buffer. Then there's another function you can register that gets called when the RPC returns. And that function also has the response buffer, of course, and it has information about whether the request actually succeeded or failed. This is most of the magic to writing Appstats, because all we do is in the pre-call hook, as we call it, we record the content of the request buffer, and we crawl down the stack to record all the stack frames and local variables. And then in the post-call hook, we match that up with the response and the error status. And then we write that to memory. This is just written to main memory. And in a typical situation, over the duration of a single request, maybe you collect a few megabytes of data. In modern processors, that's absolutely not a problem. At the end of the request, we gather all that data that we've collected, serialize it, and write it to Memcache. And so, of course, we practice what we preach. We write two different pieces of information to memcache. We write a short summary record that is used by the summary page. Let me see, what is the summary page? This is the summary page. So it has information about a whole bunch of different requests. So the way it gets this is by crawling memcache, looking for every single summary record. Because so the summary records have to be small, because memcache doesn't give you a way of, say, only return the first 100 bytes of each record. On the other hand, the long details record, of course, is used to reconstruct what you see in this page, which has much more information. Look at all those stack traces. There's a lot of data there. Anyway, this data is written to memcache. That's the end of the information gathering stage. Then later, at your leisure, as long as it hasn't expired out of memcache, of course, you point to your browser at the UI, which I mentioned before, and the UI just gets the information from memcache and displays it. It's a little Django template-based application. It's actually very simple. Now everyone's question, and I know this was the first question that showed up on the wave a few days ago, actually. What is the overhead of Appstats? Well, I was interested in this myself, so made sure that I could figure it out. First of all, the callback functions that are used to record the information actually sort of start a separate clock ticking when the function is called and when the recording function itself is finished recording. And so we keep track of how much time we spend recording. And we log that at the end of the request. We also log how much time it actually took to write the complete set of data to memcache. So I highlighted as every request that actually has Appstats activated logs one line in the application logs. And you can see this very easily in the administration console, but just by going to logs and clicking on show all records with level info or better. And so you'll see these messages that say saved. That just means something was saved by Appstats to memcache. It actually, for debugging purposes, mostly shows the memcache key. Then it shows the size of the small record it wrote. The summary is typically maybe 100 bytes, 150. Then it shows the size of the full record. 100K is pretty typical. Then it shows the overhead. So in this case, we only spent 4 milliseconds recording the data, but then we spent another almost 50 milliseconds writing that data to memcache, because serializing 100K takes a little time. It also actually logs a link back into the Appstats UI, if you've done it right. Now let's do a little calculation. How much data is this going to put in memcache? Now it's important to understand that Appstats doesn't sort of record an infinite amount of data in memcache. That would be bad, because we'd sort of be pushing all your application's data that is useful for actually making your application faster. We'd be pushing that out of memcache if we filled it up. So we actually only record the most recent 1,000 requests. The way we do that is actually by cleverly hashing the timestamp of the request to a memcache key. And so all the requests, at some point, those keys start rolling over, and you'll just be overwriting old logs. And of course, the actual timestamp is also contained in the record, so the UI knows that the UI knows that what the actual time was. It doesn't only have the hash of the time. So if we store 1,000 keys, and a typical key stores about 100 kilobytes of data, that would be 100 megabytes. In the grand scheme of memcache, that I wouldn't call that a drop in a bucket, but it's certainly not very much. The typical amount of memcache data that you're allowed to have is much larger than that. So we'll still have the question, so well, is it fast enough if my application is super extremely popular? Now, Rietveld is not super extremely popular. It has maybe one or a few QPS in the best of cases. For readfelt, we've turned it on, I think, about half a year ago, and we've never gone back. We've just kept it on all the time, and it works great. But actually, I looked recently at the logs, and the typical request, about 20 milliseconds at most, is attributable to overhead. So since the typical request in readfelt takes about half a second to run, that is not important at all. Now, if you have a very popular application, if you're like 100 or 1,000 QPS, you might not want to store data about every single request. First of all, you've probably already done some optimization to get to that level of QPS. But moreover, if you're only saving the 1,000 most recent requests, you'll end up having a fairly random sampling of requests anyway. So what you can do there is actually use a specific configuration parameter for Appstats that lets you say only record randomly, say 1% or 5% of all requests, or 0.1%. And by using that, you'll sort of completely reduce the amount of overhead that Appstats applies to your application, because it's like the overhead for one request times like 1%, which is almost nothing. Now, if you want to know how much this costs, 20 milliseconds every second, for example, I think would be under $1 of CPU time or so. So even if you turn this on, and I'm not sure I'm even doing this calculation right, but I did look at how much you would actually paying in dollar cost for this, and it's only a very small amount of money each day, even if you turn it on full speed. So I wouldn't worry too much. At the same time, you might try it out first in the SDK. When I first wrote the tool, I actually learned more from pointing it at my application when running in the SDK, because even a single request, it was so obvious which things I was doing wrong that they didn't even have to run it in production for a long time. So if you want to configure Appstats, in Python, it's 4 lines of Python code that you can literally just cut and paste from the documentation. There's no additional tailoring for your application required. You put these 4 lines into a file named appengineconfig.py in the top level directory of your application, and deploy your application, and now the application is recording, and you can check the logs in the admin console. Make sure to look for info level logs, and you can check that it's actually saving stuff. To be able to view the user interface, you have to add these 2 lines, again, literally these 2 lines, to your app.yaml file, and then point your browser to /stats. If somehow /stats is already a URL in your application, you can actually map it to something else, as long as in the end it ends in stats. Oh, and the UI script is smart enough to only let administrators access this data, so you don't have to worry that your users are going to look at the statistics of your app and figure out the DOS attack or something. In Java, the mechanism is different. It's adding 10 or 20 lines of XML. The basic idea is the same. Very simple cut and paste, redeploy, and you're in business. And for details, see the Java documentation. Just type Java App Engine Appstats in your browser, and you'll find it. For Python users, there's one caveat. When we first released 2 years ago, all our documentation had, as an example, sort of in their Hello World example code, something called WSGI handler, CGI handler, as the way to sort of start your application, assuming your application is using the WSGI framework, which all Python apps pretty much do, all Python web frameworks. That doesn't actually work right. There are some other reasons why WSGI refs handlers is not a good thing to use. So there is a web app specific function, run WSGI app, that you have to use. And even though you import this from web app, which is App Engine's own sort of miniature web framework, it doesn't mean that you have to use that web framework for the rest of your application. You can still use Django or whatever you like. So there is more you can do in the configuration. And I'm actually not going to say that much about this, except that you should download the SDK, search for the Appstats directory, and then in that Appstats directory find a file named sample-app-engine-config.py, and it has commented out blocks of configuration variables with explanations of exactly why they are there. And using this, you can sort of change things like the key rotation scheme. If you want to spend more memcache space to say, for example, 10,000 keys, you can change the key rotation scheme. If you want to reduce the space used up for stack frames, you can sort of change the maximum stack depth that is recorded, or how many variables per frame, or how many bytes to store for each variable maximally. You can tell it to skip certain frames, or you can tell it to select only certain events. And the randomized fraction of all events is actually a special case of that. You can select on things like what user was logged in, or what IP address did it come from, or the presence of a certain query parameter, or anything else you can gather out of the request headers, actually. And then there's the path normalization, which is probably best shown by looking at this. So these X's are put in by a little function that does path normalization, because in Rietveld, every issue has its own URL, but we want to sort of, the same code is responsible for those, of course, so we want to map all these to the same key, and so /12345/div/1/2 is mapped to /x/div/x/x. And let's look at the other guy. I lost it, doesn't matter. Okay, so that's the stuff you can do with advanced configuration. And I see we have almost half an hour left, so say 10-15 minutes for questions. That gives me 10-15 minutes for some specific performance issues. And first, I want to get on my soapbox and say, if you ever wrote an App Engine app, there is most likely a performance issue in your app that you're not familiar with. And the reason is that when you're sort of testing your app, you're thinking much more about correctness than about performance in most cases. Now, of course, after correctness comes performance, but I hope we've all learned that thinking about performance before you've even reached correctness is ludicrous. So things like unit testing frameworks make it very easy to check for correct working of your application, not so easy to check for sort of maintained performance characteristics. So typical testing procedures, whether it's manual testing or automated testing, doesn't really look for performance issues specifically. Also, often the performance issues are sort of a little bit here, a little bit there. Two gets you could combine into one here, a get over there that you don't need at all, or only in certain cases there. And it's hard to sort of tell the difference between my app is slow because, well, yes, I'm using it on the internet. Of course, the internet is sort of, sometimes it's slow. It could be the wireless in the building. It could be some piece of server infrastructure that you have no control over. Or maybe your application is actually doing something very inefficient with remote procedure calls. All those things sort of blur together, so you don't necessarily look at that. So here is, in a before and after picture, quickly why it matters. And this is actually from a blog by Jens Scheffler. This was a very simple demo app, and the first version takes about almost 400 milliseconds real time to execute. And what it does is it fetches 20 objects from the data store, one at a time. So it's a for loop, and in the for loop is a data store get call. And the second version, which performs exactly the same amount of work, it also gets those very same 20 objects, but it uses a single batch RPC to pass 20 keys to the data store at once. And now it only takes 200 milliseconds to execute. And sort of an indirect proof that this is actually doing the same thing is the red bars. The red bars represent how much you're being charged for all those data store operations, and to some extent for the CPU in your application. So the red bar here is about 500 milliseconds long, meaning that you're charged 500 virtual milliseconds for those operations. And here it's actually 440. That's, I think, within the natural variability of the cost of requests. But because the data store is actually fetching the same 20 objects for you, it's natural that you're being charged the same amount. However, it's doing it twice as fast in only 200 milliseconds rather than 400. So your users see a huge improvement. And so this is always important. So issue number one, and this is sort of the most basic one. This is where you start off when you're first looking at performance for an app that you haven't looked at performance at all. The problem is you don't actually know what to cache. So what do? Well, you could start thinking about it, sort of analyze what requests are the users making, and try to follow the code path through your application. And very quickly you get lost because you don't actually know if it's taking this or that branch of a particular if. What you do instead is you link your application with Appstats, configure it, run it, and now you'll see immediately which parts of your application are making the most RPC calls, and now you know where to start optimizing. And often you didn't even know that every single request was touching a certain part of the data store. That's one of the things that always surprises me. How many sort of hidden requests are in some generic piece of code that you sort of forget about because you wrote it on the first day of development. So now you start adding some caching code, and the second bug, and this is actually a state that I have to admit that shockingly when I started looking at RPC performance, Rietveld had actually been in this state for about 3 months. We had sort of done some analysis of where is it slow without Appstats, and we had put some caching in, and we had actually made the right guess about where to put the caching in, and the caching was completely working. Except after we successfully retrieved an object from the cache, we were also still retrieving the same object from the data store through some little bug in a Boolean variable that was not set correctly, or a function that wasn't returning the right true or false result. We had not thought of this possibility in the code. We had actually checked. We thought we checked that the code was caching correctly by putting various log messages in. So the log showed us, yes, it's retrieving the value from the cache. It's working. We didn't actually go to the point of measuring, was it also faster? And Appstats immediately pointed out that it wasn't. So a very specific case of that, this came up a few weeks ago in a simple internal app that a colleague wrote. This is typical caching code. You try to get something from memcache. If it's not in memcache, then you try to get it from the data store. So in this case, what we're getting is actually a query. We're asking for all state objects with a certain property. And to sort of protect the innocent, I'm not showing what the name of the property was. Then we put the result in the data store, and then we start iterating over the results. Well, what you forget, except if you can see it if you look at the bottom of the slide, is that this is not actually storing the query results. This is caching a query object. A query object is just a little piece of memory that stores what things to query for. It doesn't actually interact with the data store directly. So this call probably took about 100 microseconds to create that query object. Then we cache that query object. And then the query object, once either retrieved from the cache or recently constructed, is used to execute the query. This is where all the time goes. The solution, of course, is to know that this sort of little pitfall exists, and by other analysis we know, and by sort of bug reports about seemingly unrelated things, we know that this is a very common bug in our users' applications. So think about whether you're actually caching query results and not query objects. The solution, of course, is to actually fetch the query results and then cache those results, because that is what the author of the code clearly intended. Caching a query object is completely useless, because computing a query object never takes more than a fraction of a millisecond. OK, so now we're getting into very different territory. Everybody loves abstraction. Everybody loves to write sort of little sub-packages that take care of a certain problem and other sub-packages that take care of a different problem, and they don't talk to each other because that way you reduce coupling between your code and then you layer other things on top of these, and now suddenly your application is very slow. And I mean, I love abstraction myself, but I also think it's very important to be able to see through abstraction and sort of look through different layers and find out why what is happening to performance. And so a typical problem that can happen is that two different parts of an application are independently deciding that they need a certain object from the data store, and they fetch it. But through completely different means, they end up fetching the same object, which means two RPCs where you only needed one if you had the proper caching. I'll leave it up to you to decide exactly how to solve that caching problem. You could change the abstraction so that those results are passed back and forth by the higher level logic, or you can put in some kind of low-level caching, write your own little in-memory caching solution. The one thing I want to point out is that the solution for this particular problem is never to use memcache, because now you're just replacing redundant data store calls with redundant memcache calls. And remember, those memcache calls still take 5 or 10 milliseconds, where you probably could just find a pointer to the object in 1 microsecond. OK, issue number 5. This is the staircase pattern that I showed at the start of this section of the talk. Just looping over data store keys and fetching items one at a time, where you could actually make use of a batch call. And this is a problem both when using the data store. It's also a problem when using memcache. Again, with memcache, and actually, in fact, with memcache in particular, because most of the time you spend waiting for memcache is actually just network I/O, fetching 100 items from memcache is just as fast as fetching one item, assuming that the result fits in a megabyte. And so use those batching APIs. Know they exist, and for the database, the typical batching API just passes a list of keys instead of a key. For memcache, there are separate multi-calls with the sort of APIs with the word multi in their name that take a list of keys and then return a dictionary of mapping keys to values. Jens Scheffler wrote very entertainingly about this in his Patterns of Doom blog. OK, I think I have 2 more. Specific case, batching external URL requests. There's not really a very simple fetch multiple URLs call, but there is an asynchronous API for URL fetch. And here, again, is a little before and after thing. Before, we were making, I think, about 5 URL fetch calls, one at a time. And you see that the total time spent there is over 1,300 milliseconds, because each of those calls is 200 or 300 milliseconds. Here, we use the asynchronous URL fetch API. You can just look that up in the documentation, or look at Jens's blog for sample code. And all those URL fetches just execute in parallel. You shoot 5 of them at once, and 5 different servers execute them completely oblivious of each other and return 5 results. And you have the same set of results in 1/5 of the time, effectively. And while you're waiting for those URL fetch calls to complete, you could even do other stuff. So if in parallel with this, so if sort of the structure of your application is, I have to fetch a bunch of external URLs, and I also have to do a bunch of data store and memcache interaction, you can do your data store and memcache interaction while you're waiting for the external fetches to complete, because these external fetches are often much more, like an order of magnitude slower than data store interactions. So the final one, and I want to mention this, but I really think you should just go look it up in Nick Johnson's blog. Nick just disappeared, otherwise I'd point him out. He was wearing a yellow t-shirt. So this is another version of the staircase of gets, caused in particular by reference properties. A reference property is a very nice thing in the DB module that lets you sort of abstract away the existence of keys in the data store and use a more object-oriented model where, for example, a blog post object has an attribute that is a blog author object. And this all works out very nicely, and you can sort of do a query, get 10 blog post results, and then pass those blog post results to a template, and the template will fetch the blog author object for each blog post and render the author's name, which is retrieved from there. This is a very nice way of normalizing your database. The only problem is that every object where there is an attribute fetch of an author object, that is actually translated into a single data store get call, because the reference property code is not smart enough to realize that you're actually going to make a similar call with a different key, or perhaps the same key, from a different post object to retrieve a different or maybe the same author object. So there you still have a staircase. I mean, you have an efficient query, and then you still have a staircase of gets after that. And Nick figured out that the right solution is to use reference property prefetching. And this is actually the simplest version of his code. In his blog, he presents two more general versions of this code. It basically requires using class properties and a special method named getValue for data store. Look it up. Just, I think if you Google for reference property prefetching in App Engine, you'll certainly find this among the first 2 or 3 hits. It is a huge improvement in your applications in many cases. So now we have time for Q&A. The clock over there says we have about 12 minutes. I have documentation links, but I'm sure a search engine will find those much more quickly. I can bring up the wave, and I'm not sure what I'm supposed to do with it. So we'll, let's see what happens if we refresh that. But in the meantime, it looks like the refresh is taking a while. If there's someone in the audience who has a question, please speak up. Is there any way to parallelize what? Funny you should ask. It isn't yet a standard App Engine feature, but there is a third-party company that has made available, and unfortunately I've sort of mislaid the name of the company, but I'm sure that searching for asynchronous data store requests will turn something up. There's an open source library that lets you do asynchronous data store requests, and I believe queries are part of that. And it's possible that we'll eventually open up the API and build that into App Engine. Let me scroll down. Oops. Okay, well, the first question, will the presentation Guido gave be available for download? I'm particularly interested in some of the parts about optimizing apps. I'd be happy to make it available. It will probably be a few days. I know that they're also recording all the sessions on YouTube, so you should be able to find it there in a few days as well. I promise if there's any way to sort of upload slides from presentations to the IO 2010 website, I'll do that. And otherwise, I'll put it in some of the App Engine specific file sections on code.google.com and post a link to the group. Okay, number 2, caching is hard to get right. Do you see App Engine adding support in their API for caching? For example, by adding a prefetch for the query to make all some field data be prefetched? That's a good idea. We have been thinking on and off about providing a higher level layer of caching, but because there are different levels of caching and there are different sort of requirements, it's really hard to write a generic automatic caching layer that works in all circumstances and for all types of applications. We're still working on that problem, but in the meantime, it's probably better to look at some point solutions like Nick Johnson's reference property prefetch. The URL for the Appstats presentation, that's really the same as the first one. What happened there? Oh, I don't know what's... Yeah, see? Let's see what happens. It's coming, it's coming. I think there was... Oh, that's a great one. Yeah. What advice do you have for users of Appstats on how to interpret the data gathered by it and how to optimize their code using the data? That's a very generic question that I actually think the best answer is watch the video of this presentation. I don't think I have like a one-sentence addition that suddenly turns you into an Appstats or optimization expert. Appstats put some overhead on the profiled application, but I am wondering how much money will it cost me if I use Appstats all the time. So I tried to mention that before. I think it's under a few dollars a day, even for a popular application. But by all means, turn it on for a little while and sort of check those log messages for overhead and do the calculation yourself. Or maybe you can, if your application is really popular, if you're in the 50 QPS club or something, you may be able to actually see a bump in your request rates and a bump in your daily usage reports.
Maybe Google can make some kinds of APIs free. This could be one of them.
Yeah, so that's a good suggestion. He suggested that some APIs could be made free. Actually, Memcache is free, sending email is free, URL fetch is free. The only APIs that we charge for is pretty much the datastore. But since Appstats itself runs as a userland library, there's no direct way for discovering whether the CPU time attributed to your application is actually spent in Appstats or in any other part of your application. So that makes that a little bit iffy. I mean, if we had a way to separate that out clearly, I would like to do that. Okay, this one we got. Oh, bringing a cold JVM online can impact Java App Engine performance. I'd imagine there are similar concerns for the Python runtime. Can Appstats provide insight into the performance hit due to factors related to the hosting environment? This is funny that you should mention this. I noticed that some Appstats requests had a very large charge for CPU time that was not sort of seemingly matched by the real time spent in the application. Like if the CPU time charged is 2 seconds more, 2 virtual CPU seconds more than the real time, and most of the real time is accounted for by RPCs. Where exactly are you spending that CPU time? And I just I looked in the admin console logs for that particular request and realized that that was a loading request. And sort of, I forget when we introduced this, but a few releases ago, we started logging a special message for every request that is identified as a loading request. And sure enough, the loading requests were the ones that had extra CPU time. So a simple enhancement that I want to apply to Appstats is actually figure out how much CPU time we've already spent when Appstats is first invoked, and then we know that that time is all spent importing the library and modules of the application. And so we'll be able to represent that graphically in a separate way, so you can say a little bit more about the cost of loading. We also have some plans for making the cost of loading an application less dramatic, but I don't want this to turn into sort of an improvised product announcement. I don't want to go into any more detail there. Let's see if there are any more questions. Many performance problems I see are deadline exceeded errors. Any way to diagnose those? That's a tricky one. I mean, if you got a deadline exceeded, there are two possibilities. Either your application is just trying to do way too much work for a single request, and then the best thing you can do is probably using Appstats, look at those requests that don't quite exceed the deadline but are very close. Because I think when you actually hit the deadline exceeded error, Appstats will not have time to necessarily save all the data. So that's not very reliable. But if you're exceeding the deadline, you're also probably likely getting close to it in other requests. And so analyzing the requests that make it to the deadline that take 29 seconds or even 15 seconds will probably be very helpful in that case. Another unfortunate reality is that sometimes if we have certain performance problems in our data store cluster, it's possible that applications sort of on average will see more deadline errors than during happier times. If those things happen to more than one or two applications, our developer relations team usually posts to the App Engine group, so you will be notified of why you were seeing deadline errors in at that particular time. Can I instrument my own code and have profiling appear in the Appstats visualizer? There is actually an API where you can create a point event that shows up with a stack trace. We don't yet have a way to, from the application, sort of indicate a start and end time for an event, but that would actually be a fairly simple thing to add to the API. If someone wants to help me by sort of proposing a patch to do that, it will happen faster, otherwise it will happen eventually. I think we're through with all the moderator questions. We have a minute left. Anyone in the audience want to add something? Contact developer relationships, because that's not supposed to happen. If a single data store write fails, and sort of at the start of the, it's not because you did a whole bunch of them, but it's just like you run a very limited amount of time, then you make one write call and it fails. If that is not due to some kind of unanticipated backend error, I'd be surprised.
Sometimes it's in the status page that shows that there's anomalies, right?
Oh, yeah.
So what do you do in that case? Just a known problem.
No two cases are actually the same. In some cases, I mean, usually our own monitoring picks up those things because we monitor things like failure rate over all applications and over specific applications. So spikes in failure rates and spikes in response times are often immediately trigger pagers, and engineers will go scurry off and find out what's going on and fix things if necessary. So it's not necessary to do something about it. You don't need to report it in general because we already figured it out. And unfortunately, we're out of time now. But I'll be available throughout the conference. Thanks, everyone.